Hello everyone, my name is Nguyen. It's a pleasure to me to present our paper, Minimize Noise in HyperLogLog-Based Spread Estimation of Multiple Flows. I divide my presentation into 5 parts. First is introduction, I will talking about the problem. Second is background and motivation, I will talking about the pivot approach and what we discover. And the next I will present our algorithm. It's called rank recovery based spread estimator. And next will be the evaluation that will show our result. And finally, the conclusion. The first one is introduction about the cardinality counting and its challenges. The counting distinct object is counting the number of unique elements or cardinality in given data stream, and it's had an application in every a log of area. It's very useful if we can finding the unique user visiting your website. You can find the unique product in your inventory. You can find your unique connection in a single source, and it can be applied all a lot of information areas such as database, data mining, wireless communication, and network and machine learning. Counting the distinct value faces many challenges. Usually the data is massive, and you have to count millions of distinct elements. Why? At the same time, you will give them limited memory, usually because of the hardware, and you cannot store all the elements on this small memory. And finally, you only had limited time. You have to read the data online, and just a single pass. You have only one chance to read it. So, how we handle the problem? In this section, we're talking about the pivot approach, including single-tenant and multi-tenant cardinality estimator, and what we discover. From that far out, we design a solution to overcome the pivot drawback. Okay, let's talking about single-tenant cardinality estimator and multi-tenant cardinality estimator. The single-tenant estimator, it can count a decent number of elements in just one dataset. Why? The multi-tenant cardinality estimator can count the distinct element of multiple different datasets. The application in the network is we can see that the single-tenant estimator can count the number of distinct destination IP in the traffic. Why? The multi-tenant cardinality estimator can count the number of distinct IP for every source IP. The state-of-the-art technique in single-tenant estimator, I can count it, is HyperLog. It's a logarithm-based probabilistic counting, and with the multiple cardinality estimator, it is virtual HyperLog. It is an independent HyperLog counting in a universal memory with a memory's random sharing strategy. And we will talking about these two techniques in the next slide. Let's talk about HyperLog. It's an algorithm-based cardinality counting algorithm, and it hasn't been proven to be correct and scalable in practice. It's using a universal register array to store the rank value. Okay, let's talk about the step of the algorithm. The first one is hash all element one by one. The hash value will be divided into 2 parts. The first part is CB is decide the number, the position we will store the rank. And the second part we will use for calculation the rank. In here, the rank is defined by the leading number 0 plus 1. It's fine in this example. The next step, the rank will be stored in the memory using the maximum function. So it's only stored the higher rank upon the location. And the last one is stochastic averaging of M to calculation the estimation of the distinct element. using harmonic mean instead of usually a normal mean to summarize the register. And just using just one big register, you can cover up to 16,000 distinct elements. Yeah, it's very impressive. HyperLogLog was designed to cause single spreader, but in many cases, a multi-tenant spreader is estimation become crucial. Of course, the straightforward solution is to dedicate memory for each spreader, but that requires massive memory. To solve that problem, virtual HyperLog using the global register array to store every spreader using the memory sharing technique. Because we are using memory sharing, so some spreader will be using the same register, therefore overestimation, and we call it noise. And the challenge is how we eliminate the noise. From our observation in HyperLog, it eliminates the noise by calculating the non-global noise, and the global noise will be divided into a portion of it will be considered as the noise estimation. As a result, the noise calculated by the global HyperLog is just constant, and it will not come up with the actual noise. In this part, I will talking about our algorithm RRSE. It's called Rank Recovery Based Spread Estimator. We will talking about our key idea to the overview and then more detail in the noise remover. Let's talk about big picture. We have a memory array here, and I will talk about encoding and decoding. And let's start with the virtual HyperLog. It starts with the HyperLog encoding, and to store in memory is using the memory sharing mapping, and to decode it is first just read from the memory, decode using HyperLog formula, and then after that it using noise remover to remove the noise. But this will amplify the memory sharing cross noise with a HyperLog approximation estimation. In our case, RRSE, we have a different approach. We have the same encoding, HyperLog encoding, and using memory sharing to store it. But for decoding, we will remove the noise before estimation, so it will avoid the noise amplification. Let's talk about the detail about the encoding and decoding process for RRSE. So in here, we using the global rank array to store the information. When the flow come in, we using half function to calculation the index and the rank of the flow. Then after that, we also maintain the global rank distribution (CM) on the fly. When we want to decode the flow, we will get the flow local rank distribution. From the global rank distribution and local rank distribution, we will recover the and calculate the recover rank distribution. Therefore, after that, we can estimate the cardinality of the flow using the HyperLog encoding. We can apply the HyperLog estimation with the recover rank distribution without changing the formula. Simply put, our goal is deliver the recovery ranks independently for every spreader by inferring the distance between the local and the original rank distribution with the local rank distribution. So the question here is how to do it. So the most important part here is how we can calculate the noise. To do this, we have to understand how the noise happens. Firstly, what we measure the rank counter of the rank I is equal to the counter of the rank I with the noise plus the noise. Then how the noise happen? The noise happen when one rank is overwritten by the higher ranks. So there is two case here. The first case is the lower rank and it changed to the current rank I. And the second is the rank I changed to the higher level rank H. So we will have what we measure now is equal to the original we measure plus the number of rank changed to the current ranks and minus the current rank and its changed to upper rank. To put it into the formula, we will have this formula with the number of the lower rank changed to the current rank is equal to the probability of the current rank plus the number of total rank lower than current rank. To calculate the higher rank, the number of current rank changed to the higher rank, we calculate the total probability of the global rank, which is more than current ranks, plus multiple with the number of the original rank. And then we have to the original formula is like this one. You can see more detail in the paper. So let me demo to show you how our algorithm is work. First, we have a global rank array, and this in here we have a local rank array with 5 elements. The global rank is have a total 12 element here. Firstly, we will calculate the local rank distribution. In here, we can see that the number of rank 0 is 1, number of rank 1 is 1, number of rank 2 is 2, and number of rank 3 is 1. Then also we calculate the local rank, the global rank distribution. I want to mention here is the global rank distribution is exclude the local distribution. So we had to minus the number of rank in the local distribution. So what we have here is from the rank 0 to 3 with the global rank is 4, 2, 1, and 0. And after that, we will calculate the percentage or the probability of this rank in all the memory. So we have the probability of rank 0 is 0.57. 1 is 0.29, and so on. The total of the probability across it will be 1. Then we apply the recover function to achieve the original rank distribution. So how we calculate? Let's apply our formula to our case. We will start with the counting rank 0. The count because there is no rank smaller than rank 0. Then the number of the counter rank 0 is equal to 1 over 0.57. This is 1.75. This is quite nearly double than the local rank 0. And from the rank 0, the original rank 0, we can calculate the original rank 1. And from the counter of the original rank 0 and 1, we can calculate the original counter of rank 2 and rank 3. And finally, what we have here is the original rank distribution. And as you can see here, the lower rank will more than the local rank distribution, and the higher rank is tend to smaller than the local rank distribution because we already recover it. Interestingly, here is the number of rank 3 is still equal to 1 because you can see the probability of the global rank distribution is there is no contribution with the rank 3. Therefore, the rank 3 we measure in the local rank distribution is also the original one. So, as mentioned previously, with the recovered rank distribution, we use HyperLog formula to estimate the spread cardinality without worrying about the memory's random sharing, which will be cause noise. Furthermore, since we perform the rank distribution recovery intendedly for each spreader, we eliminate the noise precisely for different size of spreaders based on the rank distribution. So in this part, we test our algorithm in a different case from attack traffic, normal traffic, and spreader detection. In our experiment, we use two datasets. The first one is waiting room traffic, and the second one is a normal traffic. The difference between here is in the waiting room traffic, the number of spreaders is quite small, but X spreader is a huge spreader. It connected with a huge number of PC. With the normal traffic, and the number of spreader is huge, but each PC is just connected to some favorite connection. So the array spreader size is just 11 compared to 9,000 in the attack traffic. With the attack scenario, we test with a different memory size from 0.5 to 2 megabit, and we compare the RRSE with the VHLL, MCSE, and the last chart will be the error chart, which is average, absolute average relative error. And you can see in the chart, a dot is equal to 1 estimation. And the guideline y equal x, the red guideline, is the reference guideline. Every estimation, the further estimation compared to the guideline, the worse estimation it is. So with the 0.5 megabit, you can see here is our algorithm is quite unbiased and accurate compared to virtual HyperLog, which is quite overestimation. Why with the MCSE is cannot estimation due to the limitation in the memory. When we increase the memory, the estimation is come to near the guideline. It means that more accurate, but still there is a gap between RRSE and VHLL, and also a big gap with the MCSE. Even with a 2 megabit, every estimation will better, but with algorithm will still better compared to VHLL and MCSE. Similar results shown in the normal scenario. MCSE is just working when they have enough memory, just for example 2 megabit memory here, and with a dense traffic. Now with the majority is a small spreader, and this is overwritten therefore by the high spreader. Therefore, virtual is difficult to eliminate the noise, and it still had an unbiased estimation. Why at the same time our algorithm is work well, and it will better with more memory come up. We also using our algorithm to detect the spreader with a threshold, and in here we using 3 thresholds from 1,000, 10,000, and 100,000. And as you can see here, the false positive ratio of the RRSE is 6 times better than the photo in 1K threshold, and it's still keep on better than the photo log. Note that because of photo log is mostly is overestimates, so the false noise ratio is quite small, crossing from 1K to 10K. We also designed a spreader detection framework on the programmable suite to test a feasible of our algorithm. So this is the architecture design in our switch. And let me talk with the encoding first. So when the packet comes in, the packet receiver will receive the flow ID from the parser. And that flow ID will be harshed by internal function, hash function, and to get the rank value and the index value. Then this index value will be used by universal recursive array, which reside in the SVD RAM to compare the current rank with the store rank. And if the current rank is more than the store rank, then the new rank will be stored. And after that, active tracker will be used to get the potential high spreader ID, which decide by if the current rank is more than predefined rank we set in the switch. And the decoder will be calculated in the control plane by the estimator. And the estimator input will come from two things. First one, it will get the flow ID from the active tracker. And the second thing, it will get the data, the rank distribution from the universal recursive array to estimation the precise spread estimator. We also do the experiment and get calculation the overhead in each step. And we finally the overhead of our algorithm in SDRAM is just less than 2%, and with the computation units it's less than 6%, and the overhead with the hash function is just 12%. To sum up, in this paper, we introduce RRSE, a fine-grained noise elimination technique for a random memory sharing based HyperLogLog. We show that RRSE provides reliable estimation under both normal and attack traffic scenario. We implement RRSE on the programmable suite and show a use case of high spreader detection. We believe that this work is open a new direction in addressing noise reduction for random memory sharing and will inspire further development in sketch-based design. Thank you for listening and have a good day.